In this video, I'm going to describe how a PTP slave synchronizes with a PTP master. Let's start by looking again at a concrete example. A network with boundary clocks, ordinary clocks, links, and ports. As we know, in such a network, some ports will be in the master state and others will be in the slave state. Moreover, to obtain a tree topology on which a master-slave hierarchy can be established, loops in the network are eliminated by having some ports be in the passive state. Now, the first thing to grasp in order to understand how the clock synchronization works in PTP is that clock synchronization actually only occurs between pairs of ports, one of which needs to be in the master state and the other which needs to be in the slave state. In this concrete example, clock synchronization would occur between this pair of ports, this pair of ports, this pair, and so forth. Let's now dive into some more details by focusing on a single pair. In a network, synchronization will obviously be achieved through the exchange of messages. So what are the messages that a master port and a slave port exchange? Well, first of all, the master periodically sends a so-called synchronization message. After a synchronization message, a master port usually sends a so-called follow-up message. The slave port that receives these two messages in turn responds with a delay request message, to which in turn the master port responds with a delay response message. An exchange of 4 messages is therefore used to synchronize a pair of ports. In a moment, we will look at how these messages carry timing information that allow the clock corresponding to the slave port to be synchronized with the clock corresponding to the master port. But before that, I would like to clarify 2 things. First, although boundary clocks usually forward messages, these 4 types of messages in particular are never forwarded by a boundary clock. Second, although in this particular example we have 2 boundary clocks, the same clock synchronization procedure is also used when one of them is an ordinary clock or when they are both ordinary clocks. Okay, let's now look at the full details of how the clocks are synced. In this figure we have 2 timelines, one corresponding to the master port and the other corresponding to the slave port. Now, let's assume that the 2 clocks are initially unsynchronized, such that the one from the master indicates 200 seconds after midnight, while the one from the slave indicates 180 seconds after midnight. So what we have is a clock offset of 20 seconds between the master and the slave. Now, a naive approach to synchronizing the clocks would be to have the master port simply tell the slave port the current time in a single message. The slave would receive that message, know that the value of the clock of the master is 200 seconds, and simply update its local clock. Unfortunately, such a simple approach does not work. The problem is that it does not take into account the propagation delay from the master to the slave, because in fact, a message transmitted from the master to the slave would not arrive at the slave instantaneously, but only after some delay. So the slave would not update its local clock to 200 seconds when the master clock reads 200 seconds, but would only do so after the propagation delay, which in this example would be 2 seconds. That is, only after these 2 seconds of propagation time, when the clock of the slave reads 182 seconds, the slave would update the value of its clock to the value of 200 seconds that it received in the message from the master. However, at this point in time, the clock of the master would already read 202 seconds. This would result in a clock offset between the master and the slave of the same value as the propagation delay. So in this example, when the slave clock would read 200 seconds, the master clock would already be reading 202 seconds. That is 2 seconds more, namely the 2 seconds corresponding to the propagation delay. So one thing that a PTP slave needs to do in order to properly synchronize its clock with the one from the master is to figure out what the propagation delay is. In that way, it could simply add the 2 seconds of propagation delay to the clock value it received from the master, which would then result in a precise synchronization, with both clocks reading the same value. Okay, so figuring out the propagation delay is one problem that PTP needs to solve. But there is another problem as well. Namely that after the master has read the value of the clock, it will still require some additional time to actually transmit a message that encapsulates that value. Moreover, this time that elapses between reading the clock and transmitting the value of the clock is usually random and therefore not predictable. And if you are asking yourselves why this value is usually random, the answer is that this might be due to several reasons. One reason are internal queuing delays within the protocol stack of the master. Or another reason might be if the communication protocol underlying the PTP protocol has non-deterministic transmissions. This is, for instance, the case when PTP is used on top of shared Ethernet, where the random exponential backoff algorithm is used. Whatever the reason, let's consider a concrete example. Assume that the time that elapses between reading the value of 200 seconds and actually transmitting a message encapsulating that value is 1 second. This means that the message will not be transmitted until this instant of time, when the clock already reads 201 seconds. This means that the message would actually not be transmitted here, but instead 1 second later. The message would therefore be transmitted with an obsolete clock value, namely 200 seconds instead of the value 201, which is when the transmission actually occurred. The slave would then not adjust its clock value to the value of 200 at this point in time, but instead 1 second later. That is, it would update its value from 183 to the value of 200 when the clock of the master would already be reading the value 203. So the offset of the clock of the master and the slave would not only be the propagation time, but also the time it takes the master to read the current value of the clock and transmitting that value. Okay, having seen that PTP will have to compensate for the propagation delay and any random delays that may occur between reading the timestamp at the master and communicating that timestamp from the master to the slave, let's now see how PTP actually works. Let us move back to the beginning of the timeline, where the clock of the master reads 200 and the one from the slave 180. As we have seen previously, the first thing that a PTP master does when it synchronizes with a slave is to transmit a synchronization message. Let's assume the master initiates such a transmission when its clock reads 200 seconds. Further assume that the transmission of the synchronization message is not completed until 1 second later, when its clock reads 201 seconds. That is, only now the synchronization message is actually transmitted. Now, the synchronization message will not carry an obsolete timestamp as in the naive approach that we discussed earlier. Instead, the master timestamps the exact transmission instant and stores that timestamp locally. On the slave side, the synchronization message arrives after the propagation delay, in this example 2 seconds later, at which time the clock of the slave reads 183 seconds. Now, the slave timestamps this arrival time and stores that timestamp locally. The next action in the PTP synchronization process is again initiated by the master. It consists in the master transmitting a follow-up message. The purpose of this message is to convey to the slave the exact point in time at which, according to the clock of the master, the synchronization message was issued. In other words, the purpose is to transmit the timestamp that the master previously recorded. When this timestamp reaches the slave stores a copy of it. As a result, the slave now knows when exactly the synchronization message was issued according to the master, namely when the master clock read 201 seconds, and it knows when the synchronization message was received according to its own clock, namely at 183 seconds. With this information, the slave can adjust its clock such that the offset between the master clock and its own clock is reduced to the propagation delay only. That is, it can adjust its clock such that the offset between the master clock and the slave clock is reduced to 2 seconds. This is achieved as follows. Basically, the slave calculates the difference between the two timestamps, which in this example gives as a result a value of 18, and then takes that result and adds it to the current value of its own clock, which in this example yields 203 seconds. This value of 203 seconds is then the corrected clock value for the slave, although without yet taking into account the propagation delay. This means that the clocks of the master and the slave are now almost synchronized. The only difference between the two is an offset of 2 seconds, which corresponds to the propagation delay. Okay, to fix this remaining offset, PTP proceeds as follows. A slave sends a delay request message, and it timestamps the instant of transmission of that message. On the other side, at the receiving end, the master timestamps the arrival time. Then, sometime later, the master responds with a delay response message. This delay response message communicates to the slave the arrival time of the delay request message. That is, it transmits the timestamp that the master recorded. The slave reads that timestamp and uses it to calculate the propagation delay. It takes these two recorded timestamps and subtracts one from the other. In this particular example, the result gives a value of 4, which is double the propagation delay. The reason for getting as a result double the propagation delay is that the master and the slave already had an offset of the propagation delay, and the two timestamps were calculated with these slightly unsynchronized clocks. In any case, getting the propagation delay is easy. We just divide that result by 2 and obtain the actual propagation delay, which is 2 seconds, as we know. Now all that remains to be done is for the slave to correct its clock value with this propagation delay. It therefore takes its current clock value and the calculated propagation delay and adds those two values together to get the new corrected clock value, which in this example has a value of 217. This value then is the final corrected value for the clock of the slave. And now the slave is perfectly synchronized with the master. And they will remain so until their clocks happen to drift apart, which will inevitably occur and is therefore the reason why PTP performs periodic resynchronizations. This is then the basic idea of how synchronization works between a master and a slave in PTP. In reality, there are a few more details, such as avoiding the slave clock from suddenly jumping forward or backwards as a result of a resynchronization. But I will not go into these details now.